Thank you very much for the opportunity to present our research to the international community. We are a research group that focuses on the use of technology to push the building industry towards a more circular economy. We are Professor Vukorep, Lukas Fritzsche, and me, Rolf Starke, from the Brandenburg University of Technology in Germany, and we cooperate with Benjamin Felbrich and his company from Munich. And as a part of our the bigger scope of our research, we developed an evaluation framework for indoor localization systems, which I will present today. Precise localization is a crucial subsection in many automation and navigation tasks. Vacuum robots, drones, cars, VR and AR headsets come to mind. And also in the building industry, localization becomes more important, but it also comes with a few particular problems. You operate in the shadow of the building, and usually you cannot utilize satellite localization, and you need to create a local coordinate system. And existing research in this area focuses mainly on the comparison of different simultaneous localization and mapping methods, so-called SLAMs, in one particular benchmark environment. Our research builds on the understanding that there is no one-size-fits-all solution to a localization task, and we want to compare different methods across different environments. The method to choose depends on many different factors. It depends on the camera data, if RGB or RGBD data is available. It depends on the availability of internal measurement units, on LiDAR data, satellite data, and last but not least, on the available computation power if you plan to use edge computing on mobile and offline devices. So our framework is not another SLAM benchmarking tool, but instead we build on existing benchmarking tools and metrics to aid researchers and developers to find the right localization method for their work. By easy integration, software integration, we hope we can push the robotic development in the architecture, engineering, and construction industry in general. In this flow diagram, you can see our framework. The software architecture is a very modular design. It consists of three main components. First, the tracking, which is providing the ground truth data. The localization, which can be any device that is able to provide a position for itself. And third, the evaluation itself, which is comparing those two over time. The three components are running in different Docker containers, which ensures scalability, ease of deployment, and the ability to change components and hardware setups later on. The ground truth, as well as the localization system, publish their measured poses as transforms in ROS2, and the evaluation component is continuously consuming those and processing them for the evaluation. Any pose estimation needs to be calculated with exact timestamps, otherwise time errors could be mistaken for position errors, and those timestamp errors can come from different sensor frequencies, from the loss of tracking, or simply from processing times, and those need to be taken into account. To demonstrate and validate the framework which I just introduced, we evaluated the localization of this wearable device. The device uses computer vision to count objects in building parts, and to prevent double counting, it needs to be able to localize itself and the detected parts. The device hardware is a NVIDIA Jetson and a Stereolabs ZX camera, and it is running the NVIDIA ISARC SLAM as well as the AirTab SLAM for this example evaluation. And for the tracking of the device, we attached 5 markers, and we installed 4 OptiTrack motion tracking cameras on the ceiling, connected them to our workstation, and to observe a tracking area of roughly 70 square meters. Here you can see the camera vision as well as the calculated position of the device. The next step is to activate the ground truth tracking position, and with a press of a key to align those 2 coordinate systems, as well as starting the evaluation calculation. On the left, we can see the visual output of our evaluation framework comparing the whole trajectory of the ground truth against the localization method, allowing even non-experts to quickly assess the performance of the localization method. But we also use more in-depth calculations. We implemented the absolute trajectory error metric and the relative pose error metric from the EVO repository by Michael Grubb. The absolute trajectory is a simple and compelling metric to calculate the position errors over the whole track, and the relative pose error just calculates the motion difference from one frame to another, or rather the accumulated motion error over multiple frames. And in our example, to prevent the double counting, it is much more important to have an internally coherent mapping than to have the exact position compared to the real world position. So in this example, we would choose the ISAC SLAM over the AirTab SLAM, even though the AirTab SLAM outperforms ISAC in the absolute trajectory error. The OptiTrack motion capturing system comes with a few limitations as a ground truth component. One good improvement for the framework would be the research into other ground truth components, because OptiTrack is difficult and costly to implement in multi-room scenarios or even building scenarios, and we didn't evaluate the accuracy of the OptiTrack system itself. Another good addition to our framework would be the implementation of easily available Bluetooth or Wi-Fi system localizations and their evaluation. Those are some of the most important setups and data sets that we were building on, especially the aforementioned Evo Python package by Michael Grubb stands out for its excellent error metric calculations. These are some of the organizations that make our research possible and that we thank for. And of course, we thank you for your attention and the opportunity to present our work, and we're looking forward very much to your feedback and your questions.